Hello everyone, welcome you all to the first session on inverse trigonometric functions of class 12 mathematics. In this session, we'll have an introduction about the concepts of inverse trigonometric functions. Now to learn a topic, the first thing what we know is we have to analyze and understand what all we know earlier, which will be helpful for us to understand the present topic. In this manner, we are going to understand what have we learned in our previous sessions, so that those previous knowledge will be able to help us to understand the present topic. Now the present topic that we have is inverse trigonometric functions. The word inverse helps us to understand that we need to know something about inverse functions. Let's try to recollect what all we have learnt about inverse functions and also trigonometric functions. We'll put it together and try to understand what are inverse trigonometric functions and their properties and everything. Inverse of a function f denoted by f inverse exists if f is 1 to 1 and onto. We have learned this in our earlier sessions on relations and functions. I hope there won't be any doubt in this. If at all there is a function, say f, which is 1 to 1 and onto, then definitely its inverse will be existing, and that will be denoted by f inverse. So this we have learned in our earlier classes. The next thing we need to know about is trigonometric functions. We know that trigonometric functions are not 1 to 1 and onto over their natural domains and ranges, and hence their inverses do not exist. You would have learned all this, and you would have a check also in your previous classes. That is, in your 11th standard you would have understood this. Now, what else we know? We know the definitions of trigonometric functions in the function way. That is, first we consider sine function. Sine function is a function which is defined from set of real numbers to the set, that is the closed interval minus 1 comma 1. That is, the domain of sine function is set of real numbers r, that is r, which is nothing but set of real numbers, whereas its range is the set containing minus 1 to 1, the elements from minus 1 to 1, or we can say the closed interval minus 1 to 1, that is all elements from minus 1 to 1 will be its range. You can easily understand this. Whatever values you give it for sine, you can give n number of values, 0, 1 degree, 2, 3, 4, anything you can give it. Everything will be lying between, all those values will lie only between minus 1 and plus 1. The maximum value a sine function can take is 1, whereas the minimum value a sine function can take is minus 1. The sine function will not range more, apart from these two values. Similarly, you can define cos function also. So we have learnt all this in our earlier classes. Now we are trying to put all those values, all those understandings in the form of function. So cos function is a function which is defined from the set of real numbers to again the set of values from minus 1 to 1, that is the closed interval minus 1 to 1. Similarly, we have the definitions for tan, cot, secant and cosecant. Tan function ranges from the set of real numbers minus the odd multiples of pi by 2. When you can see 2n plus 1 into pi by 2, this means that they are nothing but odd multiples of pi by 2. So the domain of the tan function is set of all real numbers excluding the odd multiples of pi by 2, whereas the range will be a set of real numbers. Easy example is, you can see that tan pi by 2 will not have any exact value. The value is undefined. So if you exempt that value, similarly if you exempt tan 3 pi by 2 and tan 5 pi by 2 and so on, you can get values for all other things. That is, you'll be able to evaluate the tan function on every other places except your odd multiples of pi by 2, and those values will be a real number. And that is why the domain of tan function is defined as set of all real numbers except odd multiples of pi by 2, whereas its range is set of all real numbers. Similarly, if you consider cot function will have the domain as set of all real numbers except n pi, that is multiples of pi, that is pi, 2 pi, 3 pi and so on. So those things will be your domain, whereas your range is set of all real numbers. You have learnt about trigonometric tables in the earlier classes. You can cross check with those values to have a better understanding about this definitions of functions. The next we have is secant function. Secant function is a function which is defined from set of all real numbers except odd multiples of pi by 2. It is similar to our tan. The only difference here is the range is not as real numbers as we have in tan. Instead, we have range as set of all real numbers minus the open interval minus 1 comma 1. Similarly, when we have cosecant function, it is also a function which is defined from set of all real numbers minus elements like n pi, multiples of pi, where its range is nothing but set of all real numbers minus of the open interval minus 1 comma 1. We'll discuss more on these functions in our next classes. Now, what else we know about the inverse functions? We'll have a better understanding about inverse functions so that it will be helpful for us to understand inverse of every trigonometric function. We know that a function f from x to y such that f of x equal to y is 1 to 1 and on to. That is, if you define a function f from x to y, if it is 1 to 1 and on to with the condition f of x equal to y, then such a function is will be having an inverse. That means that you can define a function, say g, which will be from y to x. That is, the domain of f becomes your range and your range of f becomes your domain. You can check that. So in this case, if you have such a function, if you will be able to define a function called a g, and that will be considered as your inverse, and it will be a unique inverse. We have discussed this in the case of a problem. We have discussed as a problem solving all these things. Now, let me go back to the definition of inverse function. So, if at all you have a function f from x to y, and if it is 1 to 1 and on to, then you can define a unique function g which will be from y to x. That is, from the domain of f to the range of from the range of x f to the domain of f, such that g of y equal to x, where x belongs to capital X and y equal to f of x, where this y belongs to the capital Y, that is from the range set. As I told you, the domain of G is nothing but range of f. Domain of G will be same as range of f, whereas range of G will be same as your domain of f, and hence we call this G as the inverse of f, and that is denoted by f inverse. Also, we have learned about composition of composition of any two functions, especially the composition of this f and f inverse. Of course, since G is the inverse of f, we call it as G equal to f inverse. So we know G equal to f inverse, and we have also found the inverse of G, and we have also got statement like G inverse is nothing but inverse of f inverse. So all this we have learned in our previous classes. We have also learned the composition of these two functions, that is inverse of f and also f. So with that understanding, we know that f inverse composite f of x is equal to f inverse of f of x, which gives you x. Similarly, f composite f inverse of y gives you y. So we can understand that these two are, that is f inverse composite f is an identity function, and f composite f inverse is also an identity function. So all these discussions we had it in our previous classes on relations and functions. So just recollect all these things. We may be using this whenever necessary. Okay, so let's understand what are we going to learn in this chapter. We have gone through what all we know, but what are we going to learn in this one? The restrictions on domains and ranges of trigonometric functions. We understood that trigonometric functions are not one-to-one and onto on their natural domains. So what if we restrict their domains and ranges? So we are going to check if at all the domains are restricted, will there be a possibility of those functions being one-to-one and onto? And if at all there is a possibility of those functions to be one-to-one and onto on those restrictions, then definitely we can ensure the existence of their inverses. So that's the next thing we are going to learn it. And the next one is behavior of these inverse trigonometric functions through graphical representations. So we are going to understand the graphical representations of this inverse trigonometric functions. And also we are going to learn some elementary properties of this inverse trigonometric functions. So these are the things that we are going to learn in this chapter with the understanding of inverse functions and trigonometric functions, provided the definitions of all those functions, everything. Now, as we said, we'll talk about the restrictions on domain and ranges of trigonometric functions. Let us consider the sine function. Now we know sine function ranges from, when sine function is defined from R to the closed interval minus 1 to 1. That is, the domain of sine function is R, whereas the range of sine function is the closed interval minus 1 comma 1. Now, as we know, the domain is set of all real numbers and the range is set of the closed interval minus 1 comma 1. What if we restrict the domain to minus pi by 2 to plus pi by 2? Now, why are we choosing minus pi by 2 to plus pi by 2? Now, when you consider the graph of a sine function, you can see that between minus pi by 2 to plus pi by 2, the value will have one complete cycle. Values of sine function will have complete a cycle there. Now, if you take any values apart from minus pi by 2 to the left of minus pi by 2 or to the right of pi by 2, the values will be repeated again and again. And hence, this is one cycle where you can see if you take minus pi by 2 for sine and pi by 2 for sine, you will have the values from minus 1 to 1. So, you can say this will give you the values from minus 1 to 1. Hence, we are restricting, we are not taking the complete real numbers. Instead, we are looking for one place where the entire cycle will be repeated, and for which I am choosing this minus pi by 2 and pi by 2. So if at all my domain is restricted to this place, it means that the function will become 1 to 1 and onto, because you will have every values, for every value in minus pi by 2 to pi by 2, there is closed interval minus pi by 2 to plus pi by 2. You will have a distinct element in the range set, that is the closed interval minus 1 to 1. Sine function restricted to any of the intervals. This is not the only interval that we can restrict to, because as I was telling you, the cycle can be defined in any of these closed intervals also. That is minus 3 pi by 2 comma minus pi by 2, minus pi by 2 comma pi by 2 as we define, pi by 2 comma 3 pi by 2, and so on. There are so many places where you can restrict your domain of sine functions, and all these domains will give you the range as minus 1 comma 1. So if you define your domain as any of these intervals, then the function, sine function at those intervals will be 1 to 1. Now when we have so many domains, now there must be something which should be called as a primary or principal. Okay, so we'll be having this minus pi by 2 to pi by 2 as the principal domain. Why is it so? Because this is the place where you will be having value shuffling from negative to positive. So between minus to plus, you will have one set of negative and one set of positive. Everything, if you take 30 degrees in the positive side and also negative side, you will have the values with the positive and negative. So when we are looking at a cycle, here is the place where we'll have values from negative to positive, and hence we call this one as a principal value. Before that, let me understand that just because we have restricted the domain of the domain of the sine function, we will be able to understand that this function will be 1 to 1 and onto, and hence sine function will have an inverse, that is inverse of sine function exists. When inverse is existing, how are we going to denote it? As we denote for f, we'll have f inverse. For sine, we'll write it as sine inverse, or we can also call it as arc sine. So these two are the definitions of inverse, denotations of inverse sine function. This is how we denote inverse sine functions. Either I can write it as sine inverse. That means sine inverse of x will be the inverse of sine function, or I can write arc sine x. So both these represent inverse sine function. So sine inverse is a function whose domain is minus 1 comma 1 and the range is any one of the intervals, that is minus 3 pi by 2 to minus pi by 2, or minus pi by 2 to pi by 2, or pi by 2 to 3 pi by 2, and so on. I hope you understand. This is nothing but your range of sine function. These are nothing but your domain of sine function. When we define an inverse function, the domain and range will be swept over here and there. Now corresponding to each branch, we get a branch of the sine inverse function, sine inverse. As I said, if you have a domain as -1 to 1 and the range is -3 pi by 2 minus pi by 2, that is one branch of sine inverse. Similarly, when the domain is -1 to 1 and the range is minus pi by 2 to pi by 2, that is one branch of sine inverse function. So you have many branches of sine inverse function, in which minus pi by 2 to pi by 2 will be called as the principal value branch. I have explained you why it is called as a principal value. And so whenever we define a sine inverse, we normally look for the principal value. If not, we'll be looking for other values also. So let us understand the notations of sine inverse in terms of sine and sine, as we have it for f of f inverse, all those things. Now from the definition of sine inverse functions, we know if at all we have f of f inverse of x, this is what we have learned in the composition functions, that gave us x. Similarly, we'll have it here, sine of sine inverse x is x, where your x lying between -1 to 1. This tells you what your x is, whether it is a domain or range. Similarly, sine inverse of sine x is equal to x, where your x lying between minus pi by 2 to pi by 2. So this is your range. In short, I can put it as y equal to sine inverse of x. If y equal to sine inverse of x, then sine y is equal to x. This is very important way of presenting it, because this will be using in solving our problems. That is, if y is equal to sine inverse x, then sine y is equal to x. Now, as we discussed about inverse functions, we have also told that we will be learning about the graph of these inverse functions also. So what are we going to have it in the graph? How are we going to graph the sine function? So it is easy to graph a sine function when it is easy to graph a sine inverse function when we know the graph of sine function. That is, the graph of sine inverse function can be obtained from the graph of original sine function itself by changing x and y axis. That is, if AB is a point on the graph of sine function, then BA becomes a corresponding point on the graph of inverse of sine function. So if you swap this A and B, you will be getting an element, you will be getting a point on sine inverse of inverse function, that is graph of sine inverse function. So it will be easy for us to graph sine inverse function provided we know the graph of sine function. So here are the graphs of sine function and sine inverse function for your understanding. Now here is a graph of sine function. You can check it out. Sine 0 takes the value 0. Sine pi by 2 takes the value 1. This is our 1. And the sine pi becomes 0. And sine 3 pi by 2 takes -1. And sine 2 pi becomes 1. I'm sorry, sine 2 pi becomes 0. Now when you consider the left side of your number line, sine minus pi by 2 gives you -1. Sine minus pi is 0. Sine minus 3 pi by 2 gives you 1. And sine minus 2 pi is -1. So this is what we have it for one complete cycle, or even more than that. We are taking from -2 pi to 2 pi. I have just discussed here. When you extend it, this will be repeated. It will not be stopping. The process will be same, and you will have the same smooth curve when you extend your real numbers. Now, what if the values are swept? That is, if at all if you consider this point, if I consider this point, this becomes pi by 2 comma 1. If at all I change this to, I consider this point as pi by 2 comma 1. When I change this to 1 comma pi by 2, then the graph which I'm going to get by flipping over this is nothing but graph of inverse sine function. You can check it out in the next graph here. Now here you can see, here is the x-axis, and the vertical one is our y-axis, y and y dash, and x ranges from -1 to 1 because this is our domain. So -1 to 1. Let's look for this value, that is 1 comma pi by 2. Where do we have it here? We have a point 1 here, for which we have a point comma pi by 2. So this is the point where we have 1 comma pi by 2. You can see that here. You can see the nature of the point on the graph of sine x. You can see how it is in sine inverse x, and you can see all other points when it is pi comma 0. Here we have pi comma 0 as a point, so that will become 0 comma pi. So do we have it here? 0 comma pi. Yeah, here we have it, 0 comma pi. So if you swap all these points, you will be getting a new graph, and that is going to be your sine inverse graph. So with this understanding, I'll try to put both the graphs on the same graph. Here it is. You can check it out. So this is our sine function. This curve is nothing but your graph of sine x, and this vertical you have y and y dash, and this is your graph of sine inverse function. Now there is a line in between these two graphs. Do you see that? And you can see a vertical line which passes through the origin, or you can say a linear graph. There is nothing but a line of y equal to x. Now this, if you consider this line, and you can see the graphs are nothing but their mirror images. You can check it out here. The graph, both the graphs are looking like mirror images having this line as a mirror point on it. So this tells us that graph of an inverse function can be obtained from the corresponding that we have already learned, and the graph of the original function and the graph of inverse function are nothing but the mirror image, or I can say they are the reflection along the line y equal to x. So when you reflect a graph along the line y equal to x, you get the other graph. That is, when you reflect y equal to sine x along the line y equal to x, you get sine inverse x, or when you reflect y equal to sine inverse x along the line y equal to x, you get sine x. So and this is the reason when we swap this a and b to b and a, we get the graph of other function. So I hope you have got some idea or a better idea about the graphs of sine and the sine inverse, the domain, their ranges, their principal values and everything. So with this understanding, I have a small problem for you to discuss in this session, and that is nothing but the problem from exercise 2.1. We can check it out. Find the principal values of the following. You had many problems in this, and I am going to discuss only about sine function, because that's what we have discussed here. So the first problem we have is sine inverse of minus 1 by 2. We need to find the principal value of sine inverse of minus 1 by 2. So let me take the given function as y. So let y is equal to sine inverse of minus 1 by 2. As we know, if y is equal to sine inverse x, then we can write sine y is equal to x. When you bring this inverse to this side, that is when you take an operation of sine on both sides, you will have sine y equal to x. Using the same argument, I can write sine y is equal to minus 1 by 2. So this means that the sine function y, that is sine operated on a value y, takes a negative value minus 1 by 2. Now let me understand the principal value of this sine inverse. Now the principal value of sine inverse is nothing but minus pi by 2 to plus pi by 2. That is, the range of sine inverse will be minus pi by 2 to pi by 2. Now in this case, where do I have this minus 1 by 2? That is, for what value of minus 1 by 2, I'll have these values as its range. So when I look into it, I can understand that sine inverse of minus pi by 6 gives me minus 1 by 2. That is, sine inverse of minus 30 degrees, or if I put it in the other way, sine of 30 degrees minus 30 degrees will give me minus 1 by 2. That is how I'm writing it. Sine inverse of minus pi by 6 gives me minus 1 by 2. I'm sorry, it is not sine inverse, it is sine of. Sine of minus pi by 6 gives you minus 1 by 2. Now when you compare this and this, that is, we have sine y equal to minus 1 by 2, and we have sine of minus pi by 6 is equal to minus 1 by 2. So this tells you that your y is minus pi by 6. But what is our y? Y is nothing but sine inverse of minus 1 by 2. This means that sine inverse of minus 1 by 2 is minus pi by 6. I hope you are able to understand. I'll repeat once again. We are supposed to find the principal value of sine inverse of minus 1 by 2. So as it is, it won't be that easy for us to understand, or I can do it, not a problem. But to make it easy, we'll take the given function in terms of y. So let y is equal to sine inverse of minus 1 by 2, which tells us like sine y equal to minus 1 by 2. That is, sine function takes minus 1 by 2. Now the sine function takes minus 1 by 2 when it is in the interval minus pi by 2 to pi by 2. That is, the principal value of inverse of sine function is from minus pi by 2 to pi by 2. So we have to look for a value in this closed interval. That is, what value of y in this closed interval gives us minus 1 by 2. That is nothing but minus pi by 6. So when sine takes a value minus pi by 6, we get the value as minus 1 by 2. So sine of minus pi by 6 is equal to minus 1 by 2. This means that from the value of sine phi y equal to minus 1 by 2 and sine of minus pi by 6 equal to minus 1 by 2, when we compare, or when we just check it out, we understand that y can take the value minus pi by 6. When y is minus pi by 6, we have y as sine inverse of minus 1 by 2. That is, y is minus pi by 6. So this tells us that y is equal to minus pi by 6. That is, sine inverse of minus 1 by 2 is equal to minus pi by 6. And we know this minus pi by 6 is a value in between this closed interval. And hence this is called the principal value. This is what we refer to, the principal value of sine inverse of minus 1 by 2. I hope you are able to understand what are we doing, what we have learned in this session. Kindly go back to your textbook and check it out, the definitions of the trigonometric functions, what we have learned now, and similarly try to understand the graphs of the other trigonometric functions also. Anyhow, I'll be discussing those functions in the next chapter also, but I won't be able to discuss every function. So I'll discuss something here and there for your understanding. I request you all to just go through all the trigonometric functions and their inverses. It will be easy for you to understand if I explain it in the next session with your knowledge. So try to understand the nature of trigonometric functions, the graphs of trigonometric functions that we have learned in 11th standard. So that knowledge will be able to help you to develop your knowledge of inverse trigonometric functions. So complete the things that we have discussed in this session in your classwork and try out this problem. Of course, I have a problem for your homework also. We can try example 1 as your homework. So complete all these before we meet you in the next session. Thank you.